We are going to take a quick look here at functional notation so that we can be a little bit more sophisticated about how we toss about relationships, equations, things like that, or more specifically, functions. A function is a special kind of relationship between variables where the restriction is that any input can produce no outputs or one output at most. You can't get two outputs from a single input. When you have that restriction, that one input will give at most one output, you have a function. Now, relationships and equations, we've been using these all along. Here is sort of building up from the basics. Oops, that's kind of off the screen. There we go. Everybody's favorite diagonal straight line, y equals x. That's the equation of a line. We know what its graph looks like. We can make it a little bit worse. Maybe we can square the x. Now we would have a parabola. Oh, maybe we add 1 to it like that. Well, now that takes the parabola and lifts it up by 1 unit graphically. And we could keep going. What we're going to do here is dispense with the identification of two named variables. We are going to toss out the y and introduce something a little bit different, functional notation. So this recipe, x squared plus 1. Man, focus is not helping me today, is it? So this identifies the relationship, the equation, as a function whose name is f, whose variable is x, and whose recipe is x squared plus 1. When we're looking at it in this format, we kind of immediately think about the graph. Y equals x squared plus 1. Oh, that's a parabola. When we switch to functional notation, you want to think a little differently about it. There is a graph for this, but we want to think more broadly. This is now basically a machine that takes inputs and produces outputs. For example, if x is 0, the value of the function is 1. Okay, so inputs give outputs. We can still do things like ask about the domain, the range, etc. All that stuff still applies. This will have a graph. It will look exactly like that, although possibly we would label the vertical axis with f of x instead of with y. So there's this new naming convention here, and I'll show you in a minute why we adopt it. F is not special. It's sort of the default, F for function. So why make things harder than it has to be? But if you're going to handle more than one function at a time, maybe you want to make up something with a different name, like, g of x is a perfectly good name for a function. Let's say that's, 1 over x, like that. Or let's say we don't want x to be a variable. Maybe we're doing a problem where time is important. So we're measuring something happening after 1 minute, after 2 minutes, and it might make more sense to use t as the variable for time. So why not? We can make a new function, say its name is h, height of a kid as a function of time, where the time is given in months. Okay, this would not be that particular function. I'm just making stuff up here, but here's a function. The name of the function is h, the variable is t. The recipe is given there, and you can now identify things like, ooh, the domain of this will be a little tricky. For example, we could not plug in t equals 2, but we could plug in t equals 9, right? That would work out. Okay, here's how this functional notation gets used. Basically, it's a story of x marks the spot, or t, if t happens to be the variable. But what it does is it gives us an input-output machine, so that we can do something like ask for f of whatever, right? X marks the spot. I'm going to unveil this. See, what used to be x squared plus 1, f of x equals x squared plus 1, I've left the x out of it to emphasize that we have an input-output engine. And basically, we query the function, we query the engine, and say, when we provide this, whatever sits in the parentheses, what do you provide back? Well, it provides back whatever that thing is, squared plus 1, right? So, for example, f of 1, well, that means go find all the x's in the recipe and replace x with 1, right? So, there. f of 1 would be 1 squared plus 1, which is 2. Okay? We can make it a little worse. We could actually plug in something that's not a number. That's perfectly fine, right? It's not so much about the graph anymore. It's about just the input-output process. This says go to your function f, and wherever you see the spot held by the variable, swap it for x squared. And so we would produce what used to be squared plus 1 now becomes x squared plus 1, or x to the 4th plus 1. And then maybe, since we've already named a function g of x, up there at the top it's 1 over x, we can actually ask for what do we get when we take one function and plug it into another. So this says go to the function f, and wherever the blank spot is held by the variable, insert the entire function g of x. And so since our function f of whatever is whatever squared plus 1, we would now produce 1 over x, which is g squared plus 1. And that doesn't simplify a whole heck of a lot. Okay, let me slide this just a little bit. Think for a second about, I don't want to get the camera out of whack. Let's see if I can do this. Can I do this? There's that function h up at the top, right? What is h of 16? Can you come back with a numerical value for that? What that says is go to the function h, that's waiting up here, and wherever there's a, one of these, replace it with a 16. So down here we would say that needs to be 1 over square root of 16 minus 7, which carried on then is 1 over the square root of 9, which is 1/3. Okay, this is how functional notation works. We can use it to plug in values and get back other values. We can plug in expressions and get back new expressions. This is called evaluating the function. Usually when we just plug in a number and get back another number, an element of the domain returns an element from the range. Or this is called composition of functions, when we actually take a second expression or a second named function and plug that in to whichever the main function is that we're working with. And there you go, functional notation.